Hey folks, welcome back to the shop. A little different project today. This is an elliptical machine that I've been trying to troubleshoot, and it's got a particular problem. The elliptical itself has two settings for resistance. One is the ramp and one is the resistance. And so this one is gonna create a different incline for the ramp, and this one is gonna change the resistance setting. Now if I'm pressing the different buttons, you can hear the motors whirling, and they are adjusting the ramp. So the angle of the ramp changes. So when this roller is riding up the ramp, it's gonna see a different resistance. And the other resistance setting, this is the normal resistance setting, and what it does, it changes the resistance within the motor. So when the elliptical is running, this large wheel is tied to one of the arms and it's running, and there's a pulley inside, and pulley drives a belt, and then the belt drives a small pulley on the end of this resistance motor. So this resistance motor, you can see there's a fairly large gear ratio between them. So the resistance motor is pretty heavy, so it's a large flywheel. And inside of this steel or cast iron flywheel, there's a copper layer. I think it's cast, maybe it's press fit. And there are two shoes here, one on each side, and the shoes have magnets. So if the magnets go closer or further away from this wheel, they're gonna generate eddy losses, and that will slow the wheel down. So there's no mechanical brakes per se, similar to what you have in cars like disc brakes or drum brakes, where you would use friction. This is basically electrical friction, electromagnetic friction, that causes that wheel to slow down, or acting as a braking mechanism. And so the adjustment is done interestingly. If you look at the panel has different resistances. So the resistance ranges from 1 to 15, and so the user just presses these buttons, and there's a computer inside, and the computer will adjust the tension. The way it adjusts the tension is with this mechanism inside here. So this mechanism has a little DC motor, and again, this is not a commercial elliptical, this is for home gamers. And this little DC motor is driving a gearbox, and the gearbox is turning an axis, and that axis has two arms here, and these arms are moving the shoes, the brake shoes, in or out. And it's really simple. So this is a DC motor, which means that you can connect positive or negative voltage to it, and depending, it will go in either direction. And to the shaft attached, there's a potentiometer here. The potentiometer has 3 leads, so it's got a high and a low end, and it's got a wiper, and you can see the wires coming out here. Okay, so the blue and the yellow go to the motor, the red, the white and the black go to potentiometer. So it's pretty straightforward. So what I did is I disconnected the wires. Again, this is the wire that comes from the motor, and this is the wire that goes to the brain box, to the electronics. And on these wires I just installed a coupler, and it's a male-male coupler, and I connected the meter to measure voltage to the two leads that would lead to the motor. and on the other side I just installed a potentiometer. This is similar potentiometer, one size larger basically than what's installed inside the little motor assembly, and this is a 10K and the one on it is a 5K. And so what I'm doing here is adjusting the potentiometer, and you can see that there's a point where the voltage just drops to 0. Okay, so it's showing 5.4 volts. So the brain box basically sensing the resistance of this potentiometer. It's a really easy and a really interesting, and I would say a cheap mechanism to have a full feedback. These motor boxes or adjustment motors or tension motor, there's multiple names for it online. They sell them for $50, but I'm pretty sure that putting them together is less than $1. I mean, this potentiometer is in the range of 10 cents if you buy this in China. The motor is another 10 cents. You have a plastic box and a bunch of gears, so it should be less than $1. Nonetheless, they sell them for 50. The original potentiometer that was in the unit was kind of shaky, so I swapped it out for a 5K. So basically the same what was in there, and this seemed to work for a while. And what I was doing, I was pressing the adjustment buttons and it seemingly worked, but it was kind of on and off. Sometimes it worked, sometimes it didn't. And so I took it apart again, and after tinkering with it I realized that you can see the voltage always positive. So if I go and hit a different level on it, so let's say we are at level 15. Now if I hit 3, you can see on the nameplate I just hit 3 and it went down to 0. So the electronics is trying to adjust the motor to move the potentiometer into the proper resistance value. So here I'm pressing 10. So you can see when I press 10, the voltage goes down to 0.1, and it's negative. It's negative voltage. So it never goes to negative 5.5 volts or negative 6 volts. So I am assuming that this thing works off of 6 volts. At least that's what I think was printed on it. Yeah, it says 6 volt tension motor. So now I'm gonna go and adjust the potentiometer, and you can see I'm slowly adjusting it. It's at the end of the turn, looking clockwise from the front. So I'm gonna go and adjust it counterclockwise. So I'm telling the brain box that resistance is different, and you can see there is a moment when this voltage goes again to 5.5 volts. I cannot attach a meter to the potentiometer right now to measure the resistance, because that goes inside the controller. It's connected to the controller, and it is basically not showing me a certain resistance, but I created a table. So when the unit is on 1 and I adjust the voltage so that the 5.5 volts that's showing now drops to 0, I can measure 1.17 kilo ohms on this potentiometer. But every time I do this, I have to disconnect the potentiometer. Now if I'm at setting 5, it's 3.1, setting 9 is 5.1 kilo ohms. So the controller is trying to adjust, but if I'm at setting 5 and I turn the potentiometer towards 5.1, then let's say it should give me positive voltage, okay, to turn the motor in a positive direction. Now if I'm turning the potentiometer to 117, then it should give me negative voltage, and you can see that never happens. So what I'm gonna do is I'm gonna press 8, which is in the center. So again, the settings is from 1 to 15, so I pressed 8, and I'm turning the potentiometer until the voltage goes down to 0. So now you can see that the voltage went down to 0. So if the controller wants to adjust it precisely, it should both apply positive and negative voltage. And you can see the voltage is always positive. If I go in the opposite direction, I can turn it all the way to the opposite direction. You can see there's a little voltage, so 0.1 in negative. So this clearly tells me that there is something wrong with the controller. Got a small 6-volt power supply. I'm gonna just hook it up to the motor, and what you can see is that the shoe is moving away, and you can also see that the resistance is changing. So it goes in, the resistance is increasing. Again, it's a function of which terminals I'm using on the actual potentiometer. If I swap the polarity, you can see it's going out and the resistance is dropping. So as far as I'm concerned, on the motor side, inside this gearbox, everything works perfectly. So we're going to take apart the electronics and look into the electronics. So this is the back side of the board, and there are 4 transistors. These are just normal plain transistors, TO92 package, and these are the lags of the transistors. So we have emitter, base collector, so these 4 will make up the H bridge. So I'm going to be measuring between these 2 feet. I'm going to make sure polarity is right. So you can see there's a diode inside. The meter is on diode, and it's showing the forward voltage of the diode, so it's 0.621 volts. And the 2 transistors on the side are the high side, the 2 in the center are the low side. So this is going to have the same polarity. You can see it's 0.621. Now for the center ones I have to change the polarity. So this one shows 162 and it's kind of drifting, 161. And then this one shows 0.605. So out of the 4 transistors, this third one is most likely the faulty. So what I'm going to do is I'm going to desolder this, remove it, and try to find a replacement. This is the H bridge that I was talking about. So on the H bridge we have the motor in the center, and it's connected to these 4 transistors. So we have the high side, and then we have the low side. They call it this way because ground is here and the positive voltage is there. And sometimes they add these diodes because when the transistors open there's a voltage peak, so they want to prevent these transistors from being blown. So that's what these are. I think they called snubber diodes. And if one of these will fail, then when the controller is controlling voltage, the positive side will still work, but the negative side will not work. Down here I made a diagram. So if I have these 2 transistors closed, then I'm going to have a positive here and negative here on the motor. So the motor is turning one direction. If I have these 2 closed, then the motor is turning in the opposite direction. So that's what the H bridge does. So Murphy's old law hit again. I have a pack of transistors. These are 15 different types, and each of them have 10 in a box, and none of them are the part number that I actually need. I actually need 2N4401 for that blow-on transistor. My buddy stopped by and he dropped off a couple of these. It's kind of similar, one can't read the number, but these are not the same. So what I did is I went in and compared the transistors. So I need 4401 and I have 5551, which you can see the material is the same. The structure is NPN, and then the most important thing is the current here. So the one that was in the machine has 0.6 and the one I have has 0.6. So I'm putting in these 5551 transistors. Here's the board, and this is the transistor I removed, and these are the 4 transistors. You can see number 3 is replaced, and basically that's how it looks like. A little taller than the other ones, but it will work. Okay, so I swapped out the transistor, put the electronics back, and you can see that did the same setup what I had before. So I have the potentiometer here, and I'm measuring voltage from the electronics on the leads that goes out to the motor. So it's disconnected, the motor is not going to get activated. But you can see there's a 5.5 volts voltage on it. So now when I'm going to turn this guy, you can see it will get to 0. So now it's in position. If I keep turning it, it will switch back to negative 6 volts. So now my H bridge is completely working. So if I'm commanding a different setting, it will go to that setting. So let's say I'm at I go back to the 0 setting, and on the main plate I'm gonna press a different number. Let's press 13. So we're gonna go to different setting. Okay, so you can see when different number was pressed, it went to negative. So the controller is trying to move the motor to that specific position. So I'm mimicking that by turning the potentiometer. So there you go. There's the value for that. So again, it's just a resistance value for this potentiometer. So I'm gonna disconnect it now and connect it back and see if everything is working properly. Connected back the wires here, so it's pretty much just one bundle of wires, and powered it up, and you can see that the braking shoe is in outmost position. So if I press 1 now, you can see the motor is churning, moving it back, and then it's got the proper feedback, everything just stops. Now I can go to position 5, which is around the middle. It's going in the opposite direction. You can see there's a little nice feedback, so it goes out and waits for a second, and then it comes back. And I can go to position 13, probably does the same. So you can see it shoots over, and then the controller will bring it back to the proper position. So it works again. Useless box, always works, except when it's not. When you're getting bored in the workshop, you can just use this. Wanted to give you a little bit more info about my past experience with this elliptical machine. About a year after we bought it, the trainer started to make basically a rubbing, a clanking noise. I took it apart to investigate, and I found the main flywheel was completely loose, and I can basically rock the flywheel on its shaft, left and right. Here's a photo of the eddy brake motor. You can see the main rotor, which is about, I'd say, 20 pounds easy, is sandwiched between two flat 1/8 plates. Here's a picture of the plate. You can see it's not that thick. There's actually 4 posts that will join the 2 plates together, but still, if you press it from the side, it's pretty flimsy. So what it will do, it will introduce a fairly low frequency side-to-side motion, and so you can imagine 2 papers like this, you know, the side plates, and the rotor is sandwiched between them, and they can move side to side. They can kind of rock side to side. And what it does, it will basically allow the shaft to move within the bearings. So you have 2 bearings on each side of the shaft, and so if these plates are holding the shaft and it's moving side to side, it is rocking these bearings. Here's a picture of the worn shaft. You can see both bearing journals are worn. Unfortunately, when I was taking apart, I managed to break the bearing housing. How cool is that? So I ended up making a new bearing housing. Here's the old one and a new one side by side. The original one was made out of plastic. You can see the new one I made is aluminum, so it's a lot sturdier. I was not able to buy the shaft from the manufacturer, and the shaft and hub assembly was around 200 bucks, pretty pricey. So I decided to make a new shaft from scratch. Easy, right? All it is just a 4-inch piece of 1/2 inch hardened stock, a couple clip ring grooves, a flat on one end, and it's done. I can basically do all that in my home workshop. The material itself is around 10 bucks from McMaster. So I ordered some 1045 carbon steel, which according to McMaster specification has about 1 thou hard nitride coating. The part number is 5936K71. Here's the picture of the assembly. There you can see it from the front and from the back. And when I pushed out the original shaft, because the end of the shaft was damaged, it damaged the hub. So it basically enlarged the hole in the hub. So now I had to make a bushing. Double press fit bushing on the shaft, hub to the bushing. You can see that the clip ring fits nicely into the groove, and here's the assembly with the new bearing housing installed. So that McMaster shaft ran for a couple months. I'd say wife was using it every day for about an hour. What happened is it completely ate through the hardened layer. So you can see, I believe this was the second shaft. I'm pretty sure this was the second shaft, because this flat that I machined was too small, and when I put the pulley on, the pulley had a tendency to walk off of the shaft. So what I ended up doing is I just bored a hole and tapped it to M4 and put in a screw, and I was able to hold the pulley in place. But you can see that it completely worn, the bearings worn into the shaft. How cool is that? So now I need to replace the bearing and make a new shaft, which, because I bought a foot of this material, I just made a new shaft. And behold, that ate even deeper into it. So here's a comparison of the first shaft, and this is the second shaft. You can see this one also had a threaded hole in the end, but the depth of the worn out material here, I'd say it's about 2.5 millimeters. So this was done in a matter of months, basically, of usage. And well, partially this is my fault, because I wasn't careful enough when I was choosing the material. But I mean, this is how you learn, right? Just reading the books is not going to give you anything. You got to go and try it. The problem with this was that this is just 1045 steel, and they have a razor thin nitride coating on it, which they sell it as a rotary shaft nitride coated. That's what they call it, and they claim it a Rockwell C60 hardness, but really the hardened layer is only a thou, so 25 microns. And it was interesting when I was cutting this. You know, my lathe was cutting when I was parting the shaft off, and then these flats I machined on my mill. So I just used the carbide tipped cutting tool, and you can see it made a good job. I think on some of these I even used shims to keep the pulley from coming off. But after these two fiasco, I went ahead and I ordered some shafting from Thompson. This one is a Thompson shafting. You can see the logo on the shaft, so this is the real deal. And this is called Thompson linear motion shaft. It's a QS half an inch L12, which is 12-inch long, and it's a quick shaft, that's what they call it. So this has a 60 case, and it's got like superior tolerance for roundness and straightness. This is made of 1566 carbon steel, and they guarantee a 1.016 millimeter case depth. So what I've done next is I basically cut two pieces off of each shaft. So one piece from the McMaster shaft and one piece from the Thompson linear shaft, and that's what you can see here. So these are mounted. This is what we call a mount. This is just plastic. You put the parts in plastic upside down, put some powder, put pressure and heat, and this plastic is going to harden. So now you have a mount. You can hold this in your hand, and you can do the grinding and polishing. And what was done here is, you know, it's going to get ground by different size paper. So we start off with 180 grit, and then you go to 240 and 320 and up to 600, and then after that we just use polishing compound. So what you can see here, this on the right side is the McMaster shaft, and there's no hardened layer. The entire cross section has the same tone. By the way, this is the picture that you can see here is after nitride etching. So once it's ground and polished, then we're just going to apply a nitride etching solution, and that is going to pop the difference between the case and the core. So what you can see here, this is the core, has a single tone, and then the case has a darker tone. So this is the same shaft, it's just the hardened layer within the shaft is going to show up in such a way. So the next thing that we can do is we come in with a hardness tester, and then we start measuring the hardness from the edge and walk in, and basically when the hardness drops, that will define the thickness of the hardened layer. So again, on this guy the hardness was around 25 microns, and then on this guy the hardness was around 1.6 millimeters. So this is what I had in the elliptical trainer for a couple years now, and didn't have any issues with it. Again, that's the difference between the two different shafts. You can see the Thompson shaft is just superior relative to this cheap shaft from McMaster. I believe the McMaster shaft was in the range of $9 or $10, and then the Thompson shaft, the 12-inch section, was around $15 or so. But there you go. Not every shaft is made equal. Hey, thanks for joining me for this little excursion into electronics, and see you next time. Bye.